For a given reaction, the activation energy, EA, relates rate constants at two different temperatures with those temperatures. This is the formulation of the Arrhenius equation that I have my students work with. You can see that in it there are two rate constants, K1 and K2, and there are two temperatures, T1 and T2. You also have the universal gas constant, R, and then E sub A is the activation energy. What we have here is we have a certain reaction which has a particular activation energy. The activation energy for that reaction is what it is. Whether the reaction is taking place in a warm environment or a cold environment, the activation energy is the minimum amount of energy that the particles need to have a chance of reacting. There is only one activation energy, but with a change in temperature, the rate constant will change. In particular, the higher temperature would have a higher rate constant. So let's do an example problem using this equation. Let's use the information in the table to find the activation energy. Let's write out the Arrhenius equation. What we need to do here is make sure that we get the temperatures and the rate constants in the right spot. In other words, the rate constant that's in the numerator on the left is matched up with the temperature that's in the lower right, and the rate constant that's in the denominator on the left is matched up with the other temperature. Make sure that you don't put something in the wrong spot. Of these two cases that were given in the table up here, does it matter which of them is the K sub 1 T sub 1 versus the K sub 2 T sub 2? No, it makes no difference. As long as you're consistent, you'll get the right answer either way. Let's just use that top bit of data as the 1 stuff and the bottom bit of data as the 2 stuff. I've gone ahead and put in the numbers. You'll note that the temperatures that have to be used are the Kelvin temperatures. These numbers that I'm circling with my laser pointer right now don't quite match these numbers that are given in the table, and that's because these have been converted into Kelvin by adding 273.15. Or if you just want to add 273, that's close enough. So now we just solve this. The left side is simply a number, and taking the log of a number less than 1 will give us a negative value for the logarithm. And then I've simplified somewhat the right side, and I trust that you can solve that for the activation energy, which is 1.59 times 10 to the 5th joules per mole, or 159 kilojoules per mole. Let's use that same information and determine the rate constant at this temperature, 430 Kelvin. There's our Arrhenius equation again. If we use the top numbers, we can put those in like so. Does it matter if we use the top numbers or the bottom numbers? No, it makes no difference. I'm just going to use the top ones. The other K value is right there. That's what we're looking for. And the other temperature is going to go right there. Now that other temperature is already in kelvins, so we should expect, and we do see, 430 right there. You can see that the T1 has been converted into kelvins. We've got the rate constant there. Perfect. Now we just have to solve this for this rate constant. This right side now is just a number. Notice that we have the activation energy. We figured that out in the previous step, and that is fixed for this reaction at any temperature. It needs to be in joules per mole, not kilojoules, so 1.59 times 10 to the 5th. If we take that and simplify it, the right side is simply a number. We now need to get rid of the natural log, so let's take what I say e to the both sides, and if you e to the both sides this, here's what you get. the natural log disappears. You get e to the 3.16102 power, which, thankfully, there are calculators, 23.5947, and you can solve that for the value of k. If we had used the other temperature and rate constant, that is the one that I had blacked out at first, you would have gotten a very similar answer, 1.05 times 10 to the negative 6th seconds to the minus 1. So it doesn't matter which temperature rate constant combination you use. Let's summarize. The Arrhenius equation relates the activation energy, E sub A, with rate constants at different Kelvin temperatures.